everyone. Welcome to RSA 2023. My name's Dan Gunner. I'm with Insane Forensics. Today, what we're going to talk about is how to improve industrial baselines. And specifically, you look at a lot of how kind of industry in multiple places is constructing baselines. And what you're seeing is some of them are still stuck in kind of the IP port protocol world, to where when you look at the intricacies of industrial control systems and when you look at what's possible, if you bring in some of that context, it's actually possible to build better ones. So that's what we're going to talk about today.
Hi,
Gabe.
My name is Gabe Weaver. I'm a critical infrastructure analyst at Idaho National Laboratory. Just want to connect the dots between the cyber realm and what's actually going on with the physical process. We think a lot of that has to do with integrating context into these baselines, and have a few ideas how we might be able to start to do that and start the conversation.
Awesome. So standard disclaimer applies, and Gabe will take it from here.
Right. So a lot of the things that stakeholders want to be able to do, at least according to the research we've been doing, they want to be able to understand what assets are on the network, and one way to achieve that is through device fingerprinting. But then at the same time, we want to understand what is normal. And the baselining really depends upon that assumption that you're able to find what normal even is. And then, how do you even consider normal? Is normal looking at different data sources like traffic or device logs? Or does it also have to do something with the physical process? So one of the neat things about operational technology is you're able to relate potentially what you're seeing in these different logs and these different data sources to actual physical process. We think that has a lot to do with impact and the so what. So you're able to communicate the so what behind why you're doing all this monitoring, why you're doing this detection, how are you going to be able to respond. So a lot of this is how do we integrate context, right? So on the right-hand side of the slide, you see are two different substations. This is from a DARPA Radix project, previous work that we published. You'll see an RTU, a switch, and 4 relays right there. One's an ABB, one's a Motorola. Are you able to do the same baseline for what is normal if you have the same events going on those networks? Maybe not. Maybe depending on your level of abstraction, you may have two different representations of the same behavior, right? So like a breaker open or a breaker close. How do you construct a baseline so that you're able to align those levels of abstraction if that's what's desired, right? So another point, maybe you have a different protocol implementation. Maybe you're using DNP3 and Modbus. How do you align those so that you're able to integrate at that higher level of abstraction? Operational context, you have seasonal processes, right? If you're, for example, if you're looking at shipping ports, that's also seasonal. Even electrical power, that can be seasonal, right? So what's normal may change depending on seasonality, and you want to be able to continually update that. Hopefully things aren't changing so fast, then maybe your process is a little wacky, right? But maybe it's consistent enough over a given time horizon that you can actually construct a baseline, but you need to be aware that could change over time. Events due to business processes, including maintenance, and then location as well. So can we explicitly represent operational context as defined by this metadata, time, events, and location to be able to facilitate construction and reduce the scope of how we're doing baselines. Next slide, please.
Awesome, and like I was saying first up, there are a lot of challenges to network-only baselines, right? As we were mentioning earlier on, a lot of them right now, depending on the vendors you look at and how they're doing it, they're building it off IP address. Some of them are building off port heuristics to say, hey, if it's port 502, it's probably Modbus. This gets trickier though, right? Because if you get to port 102, right, and suddenly you're in S7COM, you're in IEC 104, you're in a very crowded port of a lot of protocols. This is where it's very, very dangerous if you're building kind of these very simple baselines, because very quickly building a baseline on port 102 is a challenge, right? And so what we're pushing here is trying to bring in more lower level observables, things at that session, presentation, application layer, things like function codes, things like actually getting into the payload, right? So baseline, right? You could take DNP3, right? Seen in North American Power Grid. It has the ability to transfer files. It has the ability to do a whole lot of other stuff over the network, right? When you look at something like DNP3, and when you want to build a baseline of behaviors on it, it's really important to get to those features, right? To say like, hey, if someone's going to move laterally through my plant using DNP3, then I'm going to set baselines on how file transfer might go through there, right? So again, that's an example to where we kind of started with current and we talked about like, hey, let's look at this protocol. Let's look at actually what it's capable of doing, and let's look at what we can bring in. At the lower levels too, you need to make sure the baselines cover not just IP, because there's a lot that goes over broadcast and multicast, right? Things like Emerson Ovation that heavily rely on those protocols. There's a lot of things you need to do when you build this. And so what we're going to present today is kind of an approach for how we do it, and we'll talk through as we go through with this. Last point on this that we're going to push at is that baselining shouldn't just be limited to the network, right? Maybe you are using passive network monitoring, but when you're building these baselines, bringing in host data is actually going to bring in a level of fidelity that gets you very quickly to that operational context, and we'll cover that a bit. When we look at historical attacks and when we look at opportunities to baseline, right? If we go back to Ukraine 2016, right, with Indestroyer, where it's sending breaker open commands with IEC 104, you have those unexpected events to where you could say like a state violation, which we'll talk about later. We'll talk about how that malware actually misimplemented IEC 104. And so if you fire that against SEL, if you fire that against other vendors, what you'll actually have on the network is an increase of TCP resets, right? It's because the malware authors themselves actually did not implement the industrial protocol itself. There are characteristics on the wire, if you're looking at that baseline, to say, hey, suddenly the malware killed the legitimate HMI or engineering workstation and stood up its own with either a worse or better implementation of it. Same with Trisis, right? When we talk about safety systems out in the Middle East, right? In that case, the attacker was actually able to get onto the safety system, again, hook the communications library on there. If we're looking at like baseline events for that, we could say, which is what the asset owner said, hey, this Trisis, this safety system suddenly wonky, it's falling over a bit. In their case, they actually called the vendor and troubleshot a few times before they actually understood that someone was on there. You can look at things in baselines like key states. So what's interesting with Triconix in the protocol is the key states actually sent over the wire in the packet. So you can look for things like, hey, the key state is in this state, or a key is in run state, and I'm seeing a program go across, right? If a program's actually able to pass in run state and not program, that might be a state you look at, right? Same deal with in controller, just different protocols. So again, we wanted to provide a few historical examples, but we're about to dive kind of deeper into how to build these.
Right, so with micro baseline, and what we want to be able to do is we have this hypothesis that maybe all these different artifacts that you see, whether it's in network traffic, whether it's in a data historian, whether it's on the device log side, and all kinds of other heterogeneous data sources, is there a higher level language that we can start to use to represent different expressions of that behavior? Right, and maybe that higher level language aligns with events that you'd expect to see in your physical process, and you can attach other metadata to that. So kind of the spiel, like just like we use high level languages to program, to do programming, grouping operations by higher level names, can we do something similar with the different artifacts that we see within the systems, and then be able to group that by behavior? And we think there's hope because in OT systems, it's more constrained by the process. We want to be able to collect behavioral features that align multiple artifact expressions of an event, like we were saying. So kind of the carrot is we want to be able to interpret these different sources of data, but summarize it in a sense in terms of these higher level layers of abstraction. On the flip side, Dan was just talking about different historical incidents that occur if you don't necessarily have the ability to construct a baseline. And you want to be able to consider what if you can't construct a baseline as well, and we'll talk about that in a few slides too. We want to view artifacts expressing operational events as a language, and so that's like in the language theoretic sense. And we actually have a work in progress paper that we submitted to IEEE Security and Privacy Language Theoretic Security, and that'll give us the sniff test. Here's kind of a sniff test on the industry side. That'll give us a sniff test on the more theoretical side as well. So we really want to be in that Pasteur's quadrant, right, where we're useful and it's theoretically interesting. We want to analyze artifacts relative to this language so we can either classify events, but then also recognize. So we want to look at behavior as it unfolds over time in a sequence of operations. And so we want to be able to model that. And are there ways to construct models of how these things are generated over time? And then if you have two different data sources, maybe you can compare those models, and that could be interesting. And we want to be able to conduct these analyses and scope the problem in terms of this explicit operational context. So if you're overfitting, maybe it's just for that particular facility. Maybe that's useful for fingerprinting. If you're a little more abstract, maybe that allows you to compare operations at a high enough level across multiple facilities. And so that's kind of the goal there. Just an outline for today. That was the motivation. That was about 10 minutes long, so we're on track, doing all right with our time. If you look on the right-hand side, you'll see the pipeline. This is research, so it's not set in stone, but it's concepts that we want to talk about. And there's also micro-baselining madness coming up after the talk over in the ICS sandbox, so we hope to get some real interaction going as well. First, you're going to start moving from left to right. We want to talk about data normalization and feature selection, right? So if you're only pulling on one data source, that's a potential single point of failure to drive the analytics. So we want to be able to incorporate multiple different sources of events as they're expressed across devices, as well as the network, as well as other sources, for example, cameras potentially. But here we're talking about network and device. We want to be able to normalize and fuse, so ontologies provide one formalism to be able to do that. We'll talk about that to be able to align things. Another way one could potentially do it is using time series. So here you're looking at how do multiple features in your data set, for example, the columns in your PCAP, if you're looking at it through Wireshark, those are features. How do you know which features to select? Maybe there's some interesting things to be done when you're doing time series analysis and be able to select features using different mathematical hammers, right? So we have intuitions about which features are useful. Are there mathematical hammers we can use to decide, hey, yeah, that makes sense, or maybe we consider this, or combinations of features too. That's kind of crazy. And then baseline construction, where we want to be able to look at behavior. We're going to talk about finite state machine inference, and to what extent can we start to understand and model that behavior of particular operational events over time. So I think we'll get into it.
Awesome. So now what I'm going to talk to is the first step of any process when you're dealing with data, which is what format should you normalize, or what format do you normalize into? And then feature selection. When we're building these baselines, what characteristics that we can even see matter, right? Because that's essentially the question which makes this hard, right? And that's kind of really the piece that's missing, that we need to move beyond just doing port and protocol level baselining and heuristics there. So starting out, right, looking at what data we have in OT environments, right? Starting from the network, we'll actually start from the bottom on this. We were talking earlier about using PCAP, and in a few slides, Gabe's going to show an example of creating features in DNP3, right? But with that, that's not the only tool, right, that we have to observe what's going on the network, right? We can see network information from NetStat, from Procmon, from logging, from other sources out there. And so building this is where, when we're looking at the different layers of network traffic that we can pull. And we can pull this at a facility level, we can pull this at a device level. Baselines don't just have to be for a single system. They can actually be for a part of your process, or even maybe for a wider part of that. So from the network side, that side's a little well known. When you get into the host side, right? Substation configuration language files, SCL files, right? These are configuration files which often kind of outline how electric utilities are set up. These are things also you can put into testing kits like Distributed Test Manager from Triangle Microworks. But using this, right, it gives you kind of a model of what the substation or what the plant looks like, right? So when you're building baselines, you might use this engineering kind of file as a diagram to say, hey, I'm going to use PCAP to see what's actually going on the wire, and I'll use the SCL file to see what the spec is, what kind of the PNID, the piping and instrumentation diagram, right? A digital version that the computer can actually ingest on that to look for differences, right? You might actually also go active on this when you're looking at transport layer and higher and go to Nmap, right? Or build Panda data frames, do this in Python. You know, look across logs, look across memory. So what we're trying to point out here is that the network is not the only source when we begin to build these out.
Right, so when you're considering multiple data sources, how do you reference and retrieve that information? And the way you start, so for example, like if we're looking at books, you know, the history of books, you used to have a citation scheme like book, chapter, section, subsection. Then when we went to physical print, we're going by page numbers. Page numbers are useful for artifacts of physical print, but maybe the logical structure of the text is what you use to be able to translate across different versions of something. And here we're talking about translating across different versions of data sources. So this concept actually comes out of some previous work we did. We vetted this at the Joint Conference for Digital Libraries. That's an IEEE conference. So the basic idea is you're constructing these hierarchies that are reference schemes, and you can even do differences of multiple versions over time, because it's important to understand what version of a data source you're using, because that will affect your analysis. So data sources you see on the lower layer, this is a cartoon, but you have XML, so that's like substation configuration language. You have PCAPs down there, and those are, you know, grouped into different types of events. So maybe you have breaker open and breaker close types of events, maybe some things you haven't seen before. Again, this is notional, it's research, right? So those are grouped into the month of January or March. Maybe it's for one type of facility or another type of facility, but we want to be able to analyze these, not just relative to the contents, but in the metadata, how are we going to reference and retrieve this and scope our algorithms accordingly to this kind of metadata. So as you mentioned before, location, time, IDA-FLIRT, I think, is kind of interesting from what I understand anyway. For binary analysis, you're grouping pieces of code based on high-level language labels or symbols, right? So that's basically you're using a hierarchy to index into lower-level data. We're doing something similar, we're proposing to do something similar with this. We want to be able to index into our data using high-level events. So this is the pipeline you saw in the outline. Essentially, you start with data, you have a network and device data, but you could have other sources of information as well. Maybe there's side channels, maybe there's energy baselining as well, maybe there's camera feeds, but you can keep saying maybe all day, so let's just start with network and device. Data normalization, as I mentioned before, allows you to fuse different expressions of concepts across different data sources. And then how do you select the features? If you're just looking at the types of fields in DMP3, you have hundreds, 200 maybe in the documentation. How do you know what to look at? And you need some mathematical hammers to help you at least have a good explanation of why you're choosing that beyond intuition. And can you learn more about your intuition as well? And then passive finite state machine inference, where you're moving beyond just selecting features and trying to find what's normal to saying, can we actually define a model that generates these events? And that can be very telling to understand what you're actually looking at in terms of how you're defining an event. Again, so we've just started this, but we're looking at DMP3. This is more general. What we want to be able to do is essentially use grammars, so language grammars, to align different types of protocol behaviors. So we have a higher level language, right? So whether you're in DMP3 or in Modbus, if you're doing an operation, you're able to look across that. We scoured the internet for different Git repositories that had some DMP3 event samples. And you can see we have select and operate versus a direct operate, and then file read, write, and delete. And certainly this isn't enough for machine learning, but maybe it's enough to start to understand the structure of what you're looking at and start to understand the function codes involved and get a feel for the types of features. So if you look on the left, that's purple. That's very important because a lot of the stuff that comes up is indexed by color. And then on the right, if you take one of those samples from select and operate, you can see just a Wireshark, just to get a feel for what we're talking about. And now this is data normalization. And it's a little bit in the research weeds, but nonetheless, if you open up one of these Wireshark samples, samples in Wireshark, and you're looking at a PCAP, you have a lot of different features, right? So you have the yellow, the gray, and the blue, and those all mean different things, and you could look at more and more kinds of things. And you're like, well, how do I even start to understand this? Because I could just treat it like a bag of things that I want to look at and aren't really sequenced in time at all. But a lot of these things, like these processes, depend upon sequences of events going well. So we want to be able to capture sequence. So maybe one interesting way, there's a paper by Bostrom and Bagnall that looked at multivariate time series. So normal time series, you're looking at sequences of events. They are occurring, unfolding over time, and you're able to have a variable that changes over that time. Here, you're just looking at multiple variables at once, and we're saying the variables are the fields in the PCAP file, but they may be other things as well. And then the way in which those things change together may be an indicator of the type of event that you're dealing with. Furthermore, they were doing gyroscopes and other types of sensors. Here, we just want to say with network and device, what are the patterns that we see? And then can we start to understand the events that are occurring based upon multiple features, but furthermore, based upon multiple data sources, network and device, because you don't want an adversary just messing right in the network without it, like maybe it doesn't make any sense, right? Like there could be something completely different going on in the device, and you're like, oh, that's fishy. But if you're only looking at one data source, you might be able to misunderstand what's going on or be led astray.
And for normalization too, something to point out that's interesting with this is where, in a lot of plants, you're not just dealing with one industrial protocol, you're dealing with multiple, right? Why we chose select and operate is it's actually you're able to manipulate breakers with that command if you know what you're doing in power plants. And so whether you're using DNP3 like we were saying in North America, or if you go over more to the Europe side where they're using IEC 104, if you're building a baseline here, your baseline's based on that breaker open. And where you begin to abstract to say, hey, if I'm building baselines on breaker open, this is also where protocols meet each other, right? And this is also where you deal with the fact that plants are going to have a lot. So the other important part of normalization is sizing down some of the intricacies of the plant, but using the grammar approach that pushing here, it helps you kind of approach that. It helps you approach that big problem and make it into one that you can apply this analysis for.
For sure. And the other cool thing about grammars is you're making explicit the lens you're using to interpret the data. And that lens is expressed as a lens. So like if you're saying, hey, that's a garbage lens, you can actually tweak it and then adjust it appropriately. So once you're able to normalize, right, like how do you know what to look at? And this is a problem of feature selection, at least, some people would say this is a feature selection problem. So how do you select the best, in some notion of best, to distinguish among classes of operational events? And, well, that might affect your analysis too, right? So if you only need a handful of features, maybe you have a better performance, ability to detect things faster or respond quicker. If you need a bunch of features and have to go offline or in the corner somewhere and come back, that also affects things too. So there's a bunch of different considerations in terms of what you define as cost when you're doing this. But we start with something simple. You got to begin at the beginning. So there's all these features in DNP3. Maybe we'll look at entropy, right? So if you have a column or even combinations of different types of columns in your PCAP file, which has the most information in the sense of where's the most surprise at. If you have a column that's just like the same thing all the time, that's going to have a lower entropy than a column that has different values, lots of different values that require more bits to be able to represent, right? So there's more information in that because you need more bits to represent all the different values that could occur in that column. And maybe if there's more information in that, it's worth looking at that feature. But you also want to scope it in terms of what's the event you're looking at. So maybe different fields, depending upon what layer in your network protocol stack you're at, maybe they have different amounts of relevance depending upon the operation that you're talking about. We certainly have some opinions, but we can actually use the math to see how it holds up. Shapelets, that's looking at, this is a little cartoony, but basically you have a time series, which is how variables evolve and change over time. The variables we're looking at are those columns in PCAPs or maybe fields in a device log. You can turn that into a number, and you want to look at patterns over time of how that thing changes. And if there's subsequences within that time series that are most useful to distinguish between different events, so you have an event, you have all the other events, are there useful sub-patterns in the sequence that allow you to say, hey, that's a select and operate, or oh, that's a file read, then that's really interesting. So, and furthermore, you can actually map it back from, we think, can map it back from that plot into actual abstract representation of packet, right? So then you get SMEs back in the loop that way. It's not just unexplainable. There you go.
So now we're going to provide kind of a concrete example because that was a whole lot of theory. So let's look at one way to build a baseline using a historical event. And specifically, we're going to use a concept called, we're going to use finite state machines. So for those not aware, what a finite state machine is, it's the fact that a lot of these systems, a lot of these controllers are in some operational state. And while they're going through operations, they get sent commands that move them from state to state. When we were looking at the Indestroyer malware, the original Ukraine 2016 malware, we noticed when we were testing it that it was actually generating TCP resets on certain RTACs found in power systems. And we couldn't figure out why. We thought, we were like, hey, maybe for some reason this is a misconfiguration on our end for some reason. We actually were working with our vendor for a while. We worked with them for a few weeks on it. And then one day we were like, hey, let's pull the IEC 104 spec that it's manipulating and see if the malware authors actually implemented it properly. It turned out they didn't. They actually screwed up part of the initial handshake. And so on certain industrial devices, when it got there, when you hit that protocol violation state, the device would be like, I'm done talking to you. You're not talking to me in a valid, kind of reasonable way. So I'm just going to kill this system. So applying this kind of concept that these machines are very simple machines in state that you can transfer, we can then take those network traces and look for situations like that. A good example of a finite state machine I always use is a traffic light, right? Traffic light, 3 very simple states, right? It's green, yellow, or red. Generally, your traffic light hopefully is going from green to yellow, yellow to red, red back to green. If your traffic light's going from green to red, definitely a state violation, right? If it's going from yellow back to green, those are kind of the high level of what you're looking at there. Where this is relevant is with IEC 104, the state machine is actually in the protocol specification you can buy from ISA or from the group that sells it. I'm drawing a blank on that. DNP3, the spec is actually owned by IEEE, so you can pay IEEE and actually get the full state machines for the DNP3 protocol. But what you can look for here, right, is that kind of, okay, if I'm expecting malware in, is the code running suddenly more out of state, or actually is the code written better and actually closer to the vendor thing to look for these differences, right? System state will also change naturally, so when vendors do push software updates, and they specifically for communications libraries, sometimes they will implement protocols slightly differently. So there are valid times where you'll see this behavior where compliance with the actual protocol is good, or where you expect that change. But in the case of the Ukraine 2016 malware, it was a bad case, right? When they dropped the malware on there, suddenly you had a bunch of state machine violations because they didn't implement it properly. So again, when we look at applying this to protocols commonly used in the power sector, right? IEC 104, it's simpler state machine. There's fewer states. There's fewer transitions. It's easier to get in there. DNP3 is definitely, right, like I said, a more complicated one. But again, these are 2 very common protocols. And when we talk about baselining, this is an example to where if you actually understand how the communication should look on the wire, you can apply something like this concept to say, okay, let me look for those differences, those slight differences to see when malware kicks off that's suddenly generating an industrial protocol out there.
Right. So finite state machine inference, what we want to do is take some of the stuff we talked about previously in the pipeline and how can we actually learn the kind of models that Dan was just talking about, right? So what is the logic behind the traffic like? Can we understand that? And so if we can do that, that's great. Maybe we have a notion of what normal is. And what's interesting, like Dan was talking about differences in implementations of the same protocol, like that can be informative as to whether you might have adversaries on a network or not. But at the same time, differences can also be a source of vulnerabilities. And so the language security community is like, we want to have consistency of that. But then you also lose the ability to do fingerprinting. So I think there's a trade-off there in the sense that you can do fingerprinting, but you may actually have the potential for more vulnerabilities too. But then if you pull in device logs, maybe there's hope yet. If no, you have a blind spot and it may require a redesign, which admittedly may not always be possible in real-world systems, but it's good to actually know where you can have a baseline and where it's not possible. And traces are similar. We consider similar if they are generated by the same or language model. I don't want to get too much into the weeds, but I do want to say that when we're normalizing the data and then processing it for finite state machine inference, there's a lot of literature that's been already done. I'll get to that in a few slides. It's been used successfully in the past. It uses a model of traces, so you're expecting kind of a client-server type of interaction where I issue a request, I'm expecting a response. That assumption is fine for the most part, but not always for unsolicited requests, for example, where you have interrupts with information going out across the networks, alerts. That doesn't hold up in this formalism. So this example where you want to loop back to the more theoretical side of the community and be like, how do you address this? Nonetheless, with this notion of traces, on the right-hand side, upper right-hand side, you have an RTU communicating to two different relays, and we're able to process that and extract traces. So it's just good to know how you're doing the analysis, being very specific about it. So if your assumptions break down, you can revisit that. And next slide. Right, and then going on to abstraction, and I think we're just gonna gloss over this a bit. There's different ways to select features. How do you abstract the request and the response? Well, that depends upon what kind of approach you're using. It could be domain expertise. It could be something like entropy. These features could, again, be combinations of different types of fields from the network and the device as well. We just want to open up the discussion to what's possible and what's realistic as well. And we think that high-level application layer fields lead to a baseline with richer semantics that generalizes, right? So if you're not too specific to the implementation or the protocol, but talking about events like break or open, now you have a shot at understanding what the actual process is going on. And it helps us to distinguish. And then overfitting, again, might lead to device fingerprinting, which is useful, but not the best. So here's an example where we took some PCAPs and we applied a passive finite state machine inference algorithm. This is just in a Jupyter notebook. There's theoretical difficulties with constructing a finite state machine, but in practice, there are ways to do this. There's protocol security flaw detection, behaviors of honeypots, and then modeling microservices. So we think this should transfer over into the OT space, especially given its more constrained nature than the enterprise type of networks. We take the information, we do an inference algorithm, and we have a sample output. We really want to have a discussion, and there's a micro baselining madness of different notions of state. So like Dan showed some state machines by the different specifications. Not necessarily every facility is going to use all possible states. So that's a further way you could constrain and define what normal is. And you might want to have states defined at different layers of abstraction within your system as well. But I'll hand over to Dan.
Awesome. And the other thing about states too is we were talking a lot about network security data, but we've also done a little bit of work of dealing with like Pi Historian and other operational data, and taking things like Pi Historian event frames, things that actually tie more to the physical process that network security people don't always look at, and trying to add it as factors to some of these baselines, right? Because kind of we see the direction and where we see the real value of this is when we can bring in not just the context of traditional security tools we get, but actually getting more towards, can we tie a cyber event to an actual operational event, right? If you can solve that gap, which that's a very hard problem right now, there's a whole lot of wins that we can have, right, as a community. So for the apply slide, what we see in the next week is just understanding how you're using baselining, right? Where are you using it? What devices are capable of it? How are they building their baselines? What is actually going on in your environment, right? That's something you can understand kind of immediately and see what might be available to you that you're not doing already. And then that opens you up for the next 3 months to say, okay, what can I do next? Where do I see value coming? Is it breaker opens? Is it something with physical security sensors that we're having? Is it something with another system? Maybe is it something across plants, right? But seeing where you think there might be an opportunity to move, right? Also identifying blind spots, identifying where you don't have data. None of us have a perfect view, right? We don't have unlimited budgets, so understanding the limitations of what you can even do with baselines. And then the next 6 months, basically kind of moving forward from there and trying to get, again, to that more operationally aware, operationally influenced baseline. Gabe mentioned resource slide, so that wraps up there. When you get our slide deck, there definitely is the resource slide that Gabe was mentioning, but with that, we'll actually turn it to questions. So any questions? And also after this, we'll be in the ICS Village area back there. If you want to talk more baselinings, as Gabe said, we're going to kind of have a small just group discussion and
For sure.
session on it.
The other thing they asked us to mention was if you have questions to use the mic because of the recording, that'd be great. But we definitely want to hear your questions.
Yep.
So you guys were talking a little bit about doing baselining not just on network, but also on host state and like historian state. So for an ICS control system that's got like 20 terabytes of host state, how do you go about doing normalization and feature extraction from a data set that large?
Yep. So good question. So some of it is going to be based on, and when you do the engineering side, right, it's going to be figuring out how much data you can collect, handle, get over there, process. We've done research on everything from having like 3 to 5 node ESX clusters to where we have like tens of terabytes of data going in. Practically, field limitations on a lot are going to be where the data is out in the field. Not everyone can actually trunk that data out of the operational environment. So it really depends on your ability to collect and process to a point. But you're exactly right to where some feeds are going to be quick, right? Or some are going to be big, right? And like we see this with like CCTV feeds, right? Because people have IP camera feeds. A lot of times they'll mask those off of security products because at the rate they send through the plant is just crazy. So for some of it, not to avoid it, it's something you engineer around. But if that, like, right, if those IP camera feeds are valuable, you might kind of do that work to be like, okay, let's extract the data we need off of it, right? Because, right, to a point, you don't want to bring too much in, but if you mask it off too quick, then you lose kind of the opportunity to deal with it, right?
Thanks.
Yeah. Cool. Awesome. Any other? Well, thanks for coming. And we'll be back there again if you want to talk baselining again. So thanks a lot.
Thank you.